SwayamPrabha. Digital India. Educated India.
In the previous class, I explained to you about phase coupling. In this context, we define the coupling parameters. First, we considered mass coupling. So, in this case, we consider a scenario like this. So, where we have a control volume within your flow that carries some particles, and the particles are having some mass exchange with the surrounding. For simplicity, we first assume that they are all evaporating, and the evaporation rate of all particles are same. Then we define this mass coupling parameter as the ratio between the total evaporation rate to the incoming rate of the carrier phase into the control volume. And by simplifying this expression, we see that this mass coupling parameter can be expressed as a ratio of the mass concentration, that is that itself is the ratio of mass of particles to mass of the carrier phase, to the Stokes number defined based on the mass transfer, that is, it is the ratio of the time scale of vaporization to flow time scale. So, this tells us that either if the mass concentration is high or the Stokes number is low, then we will have higher mass coupling parameter, and in that case the mass coupling between the two phases may not be negligible. So, in a similar way, we can define momentum coupling also. So, we do a similar analysis. So, in this case, the momentum coupling parameter is basically the ratio of the drag force, total drag force on all particles to the incoming momentum of the carrier flow. So, now this can be expressed as the following. So, the total drag force is basically equal to drag force on individual particle. Here we assumed Stokes drag times the number of particles. Number of particle is number density times L cube, the volume, and the momentum of the carrier phase is basically equal to mass flow rate, that is rho L square U, that is the mass which is coming in, times the velocity. So, that is why you have this rho C over bar L square U square. Now, like the previous case, in this case also we can multiply and divide with the mass of individual particle, which is basically equal to density times the volume of each particle. Then we can show that this expression is basically equal to this, and then the mass coupling parameter is essentially equal to the ratio of concentration and the Stokes number based on momentum exchange times you have this extra parameter here, that is 1 minus the ratio of the velocity of the carrier phase, velocity of the particles to the velocity of the carrier phase. And in this case, the definition of Stokes number is basically the general expression for Stokes number that we usually use, that is the ratio of the particle relaxation time to time scale of the flow. So, in this case also, if we have the carrier phase and dispersed particle velocities similar, then we can replace concentration with the mass loading ratio. So, here again we see that, means obviously if the number of particles or concentration is high or the Stokes number is low, then we have the momentum coupling parameter significant. Now, what does this physically mean? What happens if the Stokes number is very high? So, if the Stokes number is high, this means that the particles don't respond to the flow. So, they will simply pass through the flow without interacting much. Okay. However, you may wonder what happens when Stokes number tends to 0. So, when Stokes number tends to 0, okay, in that case what happens? That you have your particle size very, very small. So, if the particle size is so small, then they are basically flow tracers. So, if they are nearly flow tracers, how it is possible that they exchange momentum with the carrier flow? So, now what happens when Stokes number tends to 0? Should this quantity go to infinity? The answer is no, because of this term. So, when Stokes number tends to 0, you have this scenario. So, in that case, you have here kind of 0 by 0 form. And interestingly, we can show that under such limiting condition, the this parameter 1 minus V by U basically is similar to the Stokes number itself. So, here you see, so because the velocity of both phases are similar, so we can also assume that the accelerations are also similar. So, now we can express the acceleration for the particle phase as this, and then take u common, and then you have this, and now this is equal to du by dt, which is nothing but u by the flow time scale. So, now you have this expression. So, you equate this to this, and we can easily show that this parameter 1 minus V by U is basically of the similar order as Stokes number. So, that is why in this case, in this limiting condition, the mass coupling parameter is only governed by the concentration. Okay. But the concentration itself will be very small even if the number is high, because in this case you can achieve this scenario when your particle size is very small, and this concentration depends on mass, and mass is proportional to d cube. So, when d itself is small, so then C is expected to be small. So, in a similar way we can define energy coupling parameter. So, here we have particles which have temperature, let us say higher than or lower than the surrounding. Let us say it is higher. Then what is the energy coupling parameter? This is the total heat transfer rate from all particles to the energy, incoming energy or enthalpy associated with the carrier phase flow. So, now this is again, this is equal to HA, temperature of particle minus temperature of carrier phase, HA delta T, times the total number of particles divided by, this is the mass flow rate of the carrier phase times CPT. Okay. So, this is the enthalpy of the carrier phase which is coming in. So, when this parameter is high, we can assume that energy coupling parameter is not negligible. So, again we can simplify, and in this case also we can show that the mass coupling parameter is equal to the ratio of concentration to Stokes number based on energy, where this Stokes number is defined as the thermal response time to time scale of the flow. We have already discussed what is thermal response time. Okay. It is the time that a particle takes to adjust with the flow such that they reach thermal equilibrium. So, now in this case also we can show that the Stokes number when it tends to 0, then the this should be energy, the energy coupling parameter is nearly equal to the concentration. But so as far as here you have solid particles, this analysis makes sense. But what happens if you have liquid droplets? Okay. Now imagine you have liquid droplets, or let's say water droplets, let's say, which are at 60 degree, they are injected into air flow which is at atmospheric temperature of 25 degree. So in that case, do you anticipate any problem with this analysis? In that case also heat transfer will take place. But the difference is that in that case you not only have heat exchange between the, or the it is not like you have the heat exchange due to temperature difference, but also due to mass transfer. When a water droplet evaporates, okay, the evaporation process requires heat, and that is supplied by the surrounding. Now this can take place even if the water temperature is close to the surrounding temperature. For example, if I put some water here, it evaporates, right? So how that happens? Okay, and when it evaporates, definitely there is heat transfer involved. Why? Because heat has to be supplied to the water, so that enough heat has to be supplied so that the latent water gets the latent heat which is required for the phase change process. So in such cases, what happens is that the heat transfer, considering the latent heat, becomes dominant compared to the heat transfer due to the temperature difference. So in that case, it makes sense to use the latent heat of the latent heat involved in the evaporation process rather than the direct heat transfer. Okay, and this is given by this. So what is md dot? That is the evaporation rate, the rate at which water evaporates. But this itself needs the latent heat, so you just multiply that. Okay, and you have and you can express it like this. Okay, so now what it tells us that the latent heat now governs this energy coupling parameter. So even if the Stokes number due to mass is high, or even if the mass coupling parameter is negligible, the energy coupling parameter may not be negligible. I hope you get the point. So this tells us that, so when mass coupling parameter is high, when it is not significant, when you have high value of Stokes number based on mass, or the evaporation rate is low. But still, because you have this factor here, so this can cause the energy coupling parameter to be high, even if mass coupling parameter is negligible. Okay. Okay, so next we will see briefly an interesting case, that is the case of equilibrium mixture, which is a limiting case. So this refers to the scenario that we just discussed, when Stokes number tends to 0. So in such case, the particles quickly achieve dynamic and thermal equilibrium with the carrier phase. because the Stokes number is small. They basically adjust with the carrier phase flow immediately. So now the question is, can this mixture be treated as a single phase with modified properties? So now the question is, can we treat this two-phase flow as a single phase flow with some modified properties? Okay. So let's see. So in this case, as we know, the mass loading ratio is nearly equal to the concentration, and we can define the mixture density, for example, as, so this is the definition of mixture density, that is the bulk density of the carrier phase to the and plus the dispersed phase, and we can express it like this, and then the bulk density of the carrier phase, we know that this is equal to the material density times the volume fraction. But in this case, the volume fraction of the carrier phase, it should tend to 1. Why? Because again, the particle size is very small. Okay. So now we can express the mixture density in terms of the material density of the carrier phase, but with some factor. So similarly, we can define mixture enthalpy. Okay. Now, why? What is the advantage with this? The advantage is that you don't need you don't need to solve separate sets of equations for carrier phase and particle phase. You can still use the same single phase governing equations, only change the properties. So that makes life much easier. Okay. So, but this is a limiting case, which is the case of equilibrium mixture, but in practical applications, unfortunately, we don't have this scenario, and we have to treat the two phases separately, and also we have to account for their interaction. Okay. And so with this, now we are finishing the first module of the course. Through this module, you were introduced to the basics of the multiphase flows, different types of dispersed multiphase flows, and the some key concepts as well as key parameters which are involved in dispersed multiphase flows. So now we will move to the second module. So we will start with analysis of particle fluid flows. Now the question is, why should we analyze particle fluid flows? What is the requirement? This is required in order to quantitatively predict the behavior of the particles as well as the carrier phase in such flows. For example, I had given one example, I think yesterday's class, where we inject some hot particles into airflow, and we wanted to predict the velocity, the temperature of the carrier phase as well as that of the particle phase. Qualitatively, we could guess some trends, but if we want actually quantitatively evaluate how the temperature of particle changes as we move along the direction of the flow, okay, what length is required, okay, for the particles to reach the temperature of the flow? What length is required for the particles to reach the velocity of the carrier phase? Should these two lengths be same or be different? What happens to the carrier phase temperature itself? Okay, so for this purpose, we have to evaluate the governing equations. We must know first of all the governing equations for the particle phase and for the carrier phase. Then we have to see if we can simplify these equations and then how to solve them. Okay, but before we look at the equations, it is important to introduce you to Reynolds transport theorem. I am sure you have come across this earlier. So, we will briefly discuss what is Reynolds transport theorem, which forms the basis for deriving the governing equations for both for fluid phase and the particle phase. Now, why this is required? Okay, so let's see this through an example. Let's say I roll a ball on floor and I want to know after what distance it stops. Then what should I do? I need to write the momentum equation, that is Newton's law. Basically, mass times acceleration is equal to the force, external force. What is the external force here? In this case, in this example, drag, frictional drag. Okay. So, if I solve this, I will know by what distance the ball stops. Now, imagine you have a fluid flow and you want to know what is the resistance offered by the floor on the fluid. Okay. So, what would you do in this case? So, in the previous case, this equation that you wrote, it is for the ball. So, you are moving with the ball. Okay. So, it is like you are on the ball when it is rolling. But in order to calculate how much force the fluid receives, or what is the external force on the fluid, you would rather calculate it at different points. You wouldn't follow a fluid particles. It's not like you cannot, but it is more difficult. So, rather, if I have a flow, let's say fluid flow in a channel, I would like to calculate, let's say at this location, then at this location, and so on. So, you stand at one location and you see what is the, you want to calculate what is the drag force there. Okay. So, this approach where we considered the ball is based on Lagrangian tracking of the particles, while this approach where you stand and you want to see the fluid flow behavior, that is called Eulerian approach. Okay. Now, Reynolds transport theorem basically provides a mathematical bridge between these two approaches. Okay. So, in one hand we have system level formulation where you track a fixed mass, that is the Lagrangian viewpoint. Then we have control volume formulation where you track what happens inside a moving region in space, which is Eulerian point of view. Okay. So, the Reynolds transport theorem, as we will see, allows us to write the conservation laws of mass, momentum, energy for a control volume, even though the underlying laws are usually expressed for a system. So, what are the main underlying laws that govern a fluid flow? One is Newton's law only, same equation, mass time acceleration is your force, it gives you the force. The other one, if I am interested in the temperature of the fluid, then I have to use the first law of thermodynamics. Okay. So, that is the rate of change of energy of a system is equal to the heat transfer minus the work transfer. That is the first law of thermodynamics. But both of this refers to the Lagrangian frame. Okay. So, we have to transform it to the Eulerian frame of reference, and that is what Reynolds transport theorem does. Okay. So, now let us look at this in some detail. We are not going to derive the transport theorem, but we will use the final result. Okay. So let's say B is any extensive property of the flow. It can be mass, momentum, energy. Okay, any extensive property means which depend on the mass. And let's say beta corresponds to the intensive property, that is per unit mass. So momentum per unit mass, energy per unit mass. Then rho times beta, where rho is the density, okay, will give us what? So you just multiply this with mass by volume. It will give extensive property per unit volume. Okay. It will be more clear if we look at the properties first. So let's say first mass. So if the property is mass, mass per unit volume is density. So in this case, what will be beta? 1. Momentum. This represents momentum per unit volume. Then what is beta? U. Kinetic energy. This is kinetic energy per unit volume. This is U square by 2. Similarly, internal energy per unit volume. This is specific internal energy. This is species mass concentration. If you have a flow where you have multiple species involved, for example, let's say flow of hydrogen and air in a duct. So each species has its own equation. Okay. So and what is this? This species mass fraction. So you see all these quantities are intensive properties. And finally, we want our equations, the governing equations in these terms. Okay. So what does Reynolds transport theorem tells us? That the rate of change of extensive property in a system, and that is what we are interested in. Okay. So for example, how the momentum in your system changes with time. So that is the rate of change of extensive property in a system, which is given by this dB by dt. Now this is equal to partial derivative with respect to time. The first term has this term plus this term. Now what are these? So the left side basically denotes the Lagrangian feature, while the right side is the Eulerian feature. Okay. So you imagine you have, so this is your coordinate system and you have a flow, and this is your control volume. Okay. So then the first part refers to the local rate of change, and the second part refers to the exchange of the property that is taking place at the control surface, at the interface between this control volume and the surrounding. Okay. So this rate of change has two components, and Reynolds transport theorem gives these two, means this expression directly. Okay. So I mean, we are not discussing how this is, how do we derive this. Okay. But we will see application of this. So in this case, this control volume can be fixed in space when we consider fluid flow. So as I mentioned, for fluid flow analysis, we have to fix the region of interest. But this control volume is a moving system for particle analysis. So if you are considering a particle which is moving, in that case the control volume itself is moving. Okay. You may ask that, okay, we are doing this transformation from Lagrangian to Eulerian for fluid flows, which makes sense. But why are we doing this for particle tracking? I mean, why are we doing this transformation for particle tracking? Can't we use the Lagrangian tracking itself? The answer is yes, as long as the control surface does not change. For example, if I throw a stone in air, I can track that using the Lagrangian system as it is. With this one, it's sufficient. But if I throw a droplet and now the droplet control volume itself reduces because it evaporates. Okay, so the boundary itself changes with time. So we have a difference there. So in that case, again we have to rely on the Reynolds transport theorem. So it will be more clear if you are already aware of the fluid flow equations without particles. But here we will see how we derive those from Reynolds transport theorem. So as I mentioned, for fluid flows, the control volume is fixed in space. So now we will use the Gauss divergence theorem. That is, we are using Gauss divergence theorem, basically we are converting surface integral to volume integral, and that is what we have done here. Okay. So if you see this part here, we have surface integral, we converted that to the volume integral. Okay. And then we use Leibniz rule to bring this derivative, this partial derivative inside. Okay. So now we have this expression for the rate of change of property in your system, which is expressed in terms of this volume integral only. Okay. Then let us consider this part, and first using chain rule we can show that this part is equal to this, and then this one can be expressed through this expression, and then I can combine these two and get this expression. What is this? This is the material derivative or total derivative. Okay. Total derivative of which quantity? Rho times B, beta, that is your property per unit volume, plus you have this quantity. So now we will use chain rule to again expand this. Okay. So and then I can combine these two terms and express it this way, and hence I can finally express the same transport theorem as the rate of change of B is equal to volume integral of this quantity. Okay. Now we will use this for mass, momentum and energy conservation equations. Let us see. So first, mass conservation. So in this case, the beta is equal to 1, we know that. So now we write this same equation that we derived in the previous slide. Now you see, this is equal to 0. Why? Why the rate of change of mass is equal to 0? Because this is according to mass conservation. Mass has to be conserved in your system, that is why it is 0. So now if I just put beta is equal to 1 here, let us see what do we get. So if we put beta is equal to 1, we get this. What do we get? Volume integral of this quantity is equal to 0. Okay. Now this means that this itself is equal to 0. Why? Why this has to be 0? So imagine you have some parameter here and you are integrating that over your control volume. So when you integrate that within the control volume, basically you are adding that parameter throughout the control volume. And if that summation is 0, why should that parameter itself be equal to 0? the summation is 0. This parameter itself is equal to 0 because I can always choose a smaller and smaller control volume. Okay, so where this equation has to be satisfied. Okay, so this means that this is possible only when the integrand has to be 0, and that is how we get the familiar continuity equation. Okay, so now once we know that this entire parameter, this itself is 0 always, then finally the Reynolds transport theorem reduces to this form. So finally you have this as your Reynolds transport theorem. Very simple equation. Now you notice that here the term density is outside this total derivative, but you should remember that this is not due to any assumption that the density is constant. This is a consequence of the Reynolds transport theorem and the way we simplified it. This does not mean that density is constant. Okay, so next we consider the momentum conservation equation. So in this case, beta is equal to the velocity. So here capital or the bold letter U signifies that it's a vector. Okay, so in this case, you just put beta is equal to U here. Okay, so this part is your transport theorem. Now according to Newton's second law, what is rate of change of momentum? External force. What are the forces? You have body force, you have surface force. Okay. Then this surface integral, we can express it again using Gauss divergence theorem as a volume integral. And then we can express it this way, and then from here it follows, we get a differential equation. From integral equation, now we have derived the differential equation, and when you solve this further, you get the famous Navier-Stokes equation. However, this one what I have written here corresponds to incompressible Navier-Stokes equation. So how do you derive this equation from this? Using constitutive relations. So what are constitutive relations? Constitutive relations means these are kind of models which relates a governing equations to the basic quantities. So here, for example, you have the stresses on the control volume or stresses at a point. Okay. However, and this is the body force. However, we need to express the stresses in terms of velocity and pressure. Okay. So the relation which provides this is known as constitutive relation. For example, here the stresses are of two types, normal stress and shear stress, and you know that shear stress is equal to mu times gradient of velocity for a simple shear flow. Okay, so this is an example of constitutive relation. This is what you have used and derived your Navier-Stokes equation. Okay, so similar way we can derive energy conservation equation and species conservation equation. So for the fluid flow, so in case of energy conservation equation, so this is your parameter beta, that is internal energy plus kinetic energy both, and then you introduce that to the Reynolds transport theorem. So now what you get is the rate of change of energy of system. Now that will be equal to the heat transfer rate minus work transfer rate according to first law of thermodynamics. Then you consider the momentum equation, multiply momentum equation with u on both sides and subtract this such that you retain the term having the internal energy only. And then we bring in enthalpy into picture, because internal energy and enthalpy are related. And then after you simplify that, you get this equation, which is valid for an incompressible non-reacting flow. Okay, so this is not a general or generic energy equation. This is valid when we have incompressible non-reacting flows. Similarly, if we put beta is equal to this species mass fraction, then we get the species conservation equation. Okay, so this is an example of incompressible non-reacting flow species equation again. So if you see, these two equations are fundamentally similar. How? You just bring in this rho Cp term here, and lambda by rho Cp is your thermal diffusivity. And what is this? This is mass diffusivity. So you see, mathematically both equations are similar. Okay. However, you will have additional terms if you consider either compressible flow and or reacting flows. For example, combustion. Okay, so you see how Reynolds transport theorem is used to derive the governing equations for the fluid phase without particles. So now we will get into our actual business, that is, how do we derive equations for particles now, and then we will revisit the equations for the fluid flow with particles. Okay, so first it is important to consider the equations for a single particle. Okay, so again we will first look at the mass conservation. Now here, so this is again the Reynolds transport theorem. Then we consider a movement of a particle in a certain reference frame. So you have some coordinate system in which this particle is moving. This particle has a velocity of v, let's say. Vi denotes one component. Okay, you can say v. Now this velocity is defined with respect to this coordinate system, this frame of reference. So for example, if you are standing here on the coordinate system, you see that the particle is moving at velocity v. The particle, let's say, has radius r, and here you see another velocity. This is the surface velocity. Surface velocity means the rate at which this control surface changes. Okay, so but what is important and interesting here is that this surface velocity is defined from the reference frame of the particle itself. So you imagine you are sitting on the particle and you are moving, and for you how the control surface changes, that is, or the rate at which it changes, that is basically this W. Okay, so now for mass conservation, again we know that beta is equal to 1. So with that, this left hand side becomes basically the rate of change of mass of this particle. Okay, now this is equal to, now you see this term, this partial derivative term is, now we are using d by dt instead of del by del t, because now we are traveling with the particle. Okay, and here this density is basically the particle density. So what does this integral denote? Integration or volume integration of rho d dv. What does it denote? this is the mass in your control volume. Okay. Now, as I said, this velocity W is defined with respect to the reference frame of the droplet. Then this term, the first term, refers to rate of change of instantaneous mass of the particle. Assuming that the density is not varying within the particle, density is same throughout. So, if you simply integrate, then what you get is, so you can take the density term outside and you integrate, what you get is the volume. Density time volume is mass. What is that mass? This is the mass. This is the instantaneous mass. So, simply this is equal to dm by dt, or rate of change of mass. Now, what is this part? This is the rate at which mass is leaving the particle. So, if we assume evaporation, you have some mass and the flux is perpendicular to the surface. Okay. And this n denotes the normal vector. Okay. So, now what from here, and this has to be equal to 0, again from conservation of mass. But from here, what do we get? dm by dt is equal to minus of this term. So, if you see intuitively, this makes sense that you have a particle which is evaporating. So, the rate of change of mass of this particle has to be equal to the rate at which it is evaporating, and that is what it is telling you. Okay. So, now if we assume that the this density, you see here I am writing rho s, it is not rho d, because what is leaving here is not the same mass. For example, if you have water, then water vapor is leaving, which has a density different from the density of water. Okay. So, that is why I am writing here rho s. So, if we assume that this fluid density at the interface as well as this efflux velocity, if they are same throughout, then they are constant terms. So, we can take them out and simply integrate, and you get the surface area. This SD is nothing but the surface area. Okay. And now you get the continuity equation for the particle. Okay. But the story does not end here. The question is, how do we get information about this? Now, what is this? What is the unit of this? Density times velocity. You have come across it earlier. This is called mass flux. So, this refers to evaporation mass flux, or rate of evaporation per unit area, evaporative mass flux. So, the question is, how do we get this parameter, or I am referring to a constitutive relation that relates this evaporation mass flux to fundamental properties of the particle. What are the fundamental properties? Particle size, particle velocity. So, how do we relate it? So, here also we will need a constitutive relation, but this represents the continuity equation for the particle.